Context you should be thinking of is, I guess, this coherent state path integral. Where we've defined an action in Euclidean time that has this Hamiltonian evaluated in the coherent state, and these field variables are coming from some second quantized operator. And that Hamiltonian can have, interacting plus non-interacting terms. So what we'll see in the next few classes and on your assignments and so on is how there's a term proportional to psi-4, where phi is a generalization of these fields in the continuum that come from these interacting terms. And what that does is it takes your exponential, if you will, or your action, and makes it non-quadratic. Therefore, you can't apply Gaussian integration directly. So that throws a serious kibosh in solving these things sort of analytically. And so what we want to do now is develop like approximation strategies for how to handle the types of terms that come from these interactions. But I'm not going to develop the psi-4 theory directly in this framework of many-body coherent state path integrals, because it's just not necessary. So what we're going to do is go back to the Lagrangian form of the action that you guys derived on this assignment that you're handing in today. So I don't have that question sheet, but I think we labeled the propagator u of x and t, so x prime t prime x t. When I develop the field theory, I want to replace these x's with q's because I'm leaving x for something else. The q's are the same, it's the position and the momentum. Okay, so the simplified, the first quantized maybe, version of this path integral is something like this, where q dot. Does that look familiar? Hopefully that's the thing you've been working on. So it's a single particle. It's the propagator. It describes the time evolution of a particle that is at position q at time t, right? And time evolves to q prime and t prime. Good. And you perform the Gaussian integration to get this in the Lagrangian form. So let's take this sort of first quantized notation and extend it to the many particle case, the thing that I claimed we never wanted to do back at the beginning of class. But we will do it just to develop this generalized psi-4 theory. So so that action, which now involves a set of coordinates. I'll probably get sloppy with notation pretty quickly here. It's just the sum of all 1/2 m v squared, if you will. We're going to have to label the q dots of each particle. And the interaction part, the v, I just want to leave as general as possible to account for, 2-body terms, 3-body terms, 4-body terms, whatever we need. And that's it. So the potential includes all interactions plus, one body or field type interactions. I don't know why I said magnetic. Just any sort of field or chemical potential or anything like that. So we'll make some assumption about the form of that in a minute. But so we sort of motivated this class in the condensed matter context by saying, the labels on these particles could be lattice sites or something like that. It could be, you could be thinking of the, Ising model where every eye labels a magnetic moment on a site, or a Bose-Hubbard model where there's sites, but then there's also particles that hop on the sites, right? And so this idea of a lattice is very inherent, and that's to condensed matter, and it's sort of what makes condensed matter field theory special. But what we're going to try to do here is go beyond that and push ourselves toward the continuum. So let's construct a field theory in the continuum limit. And I'll justify this a little bit after we do the construction in retrospect. But you should maybe start thinking, why would I do this if I have a crystal of maybe 3-dimensional crystalline material that has a lattice, right? So there's good reasons for doing this. But let's just imagine taking the continuum limit. And I will take this coordinate, Q, and as is standard in field theory, I'll replace it with a field variable, which I call phi. And then this lattice site, I, which could be labeling the particle explicitly, is what is going to go to the continuum position X. So that's why I replaced X with Q in this single particle path integral here. that functional integral. So every phi now is a field which lives in whatever d-dimensional space and varies with its position in space. Okay, so it's just a continuum, a continuous variable. So I would say this goes to phi x of t now. And the time dependence I'll just basically drop because it's implicit. It's implicit, I think, in the action, which has an integral over time. Okay. But just remember, this is the field that's time evolving. Let's see, and I also have a sum over all my particles here. This is an n particle case. I have a sum over my particles, but in the continuum, that sum has to turn to an integral. So in d dimensions, they look like this. Well, remember, what I've sort of done is imagine taking a lattice that has a lattice spacing delta. Right, so maybe that's xi minus xj or something like that. So that discrete sum just turns into an integral in d dimensions. I'll actually write the psi-4 theory in 2D, just to be explicit. So in 2D, this would just be 1 over delta squared. So in this picture, my sum just turns into that integral. Then, for example, this kinetic energy term, the first part of the action that doesn't depend on the potential. So what is it? It's sum I so let's just do it in 2D. So I need the phi derivative now with respect to, time. Q, I forget the dot. Oh my God. Question?
Yeah, why do we keep the lattice spacing in the continuum case? Where's the delta still there?
It's a good question.
Doesn't it go to 0?
We'll see what happens if we're going to scale it out of the problem, but it's what's called the UV cutoff, the ultraviolet cutoff of the theory. And in order for theories not to explode sometimes, you have to regulate or you have to do something with that delta. Okay. It'll occur in like a limit of your integral quite often. It's like it'll go from delta, some UV length scale, some IR length scale. And so, I mean, in order just to define the derivative, you need that thing right here, right? But it goes, I'm just leaving it in the problem. I'm going to rescale all my fields by it in a minute. So just always be aware that there's some subtlety in this procedure of going to the continuum, and we'll encounter it a bit later. And this thing, we'll just call the UV cut. We'll call the UV cutoff. I'm going to scale it right out of the problem right now. So that's your kinetic energy piece. Oh yeah, this sigma is exactly what we're talking about here. So we have all these masses, and I have this integral, and I have this delta. So I've just defined in this case a mass per unit area. Assuming that all the masses are the same. Okay, so I'm starting to make this a little less general. By saying that all mi's are equal to some mass And this is just a mass per unit area. Okay, so part of that delta is keeping your units correct too. Okay, so we could rewrite our action with this new kinetic energy. One more step that I want to take is, before we do that, is just looking at this potential and writing it as a sum of all these n-body terms. What do I call it? Q1. And we'll essentially look at the lowest order, most interesting piece. So let's imagine we're on a lattice like this, and we're taking this lattice of the continuum. So on the lattice, the lowest order interaction that we'll be interested in is basically going to be something like this. Remember this angle bracket, IJ, angle bracket means nearest neighbors on a lattice. Okay, so I've just written an interaction term, all right, parameterized by Hij. So who knows what this thing is? This has to come from your microscopics. Where Qi and Qj are related by Hij for every single nearest neighbor pair. And then I can, like this would be the analogy to like your Ising interaction or your Heisenberg interaction or something like that. And then you can imagine having higher order terms. Again, generally coming from the microscopics or conversely the symmetry in the problem. Okay, so let me write this Qi.Qj. J dot. There's Qi squared minus Qj squared. Q. Okay, that's not quite right. What am I missing? It might be a minus 2 here. Whatever. So up to some minus 2. I'm writing this thing as a difference of squares, subtracting the individual squares. So for these pairs of particles, in a continuum, I can write this thing here. Qi squared minus Qj squared, which is the finite difference. Wait, oh, I did this totally wrong. This is square root outside, sorry. Square outside. That's what I want. It's the simple things. Right, so that's the thing that looks like the square of a finite difference. That's the derivative. That's what I'm trying to do here. So this thing is, in the continuum, the field derivative. Remember this, and this delta, right? So the derivative is defined as Qi minus Qj over, like, say, xi minus xj, right? And xi minus xj is just delta. It's just the lattice spacing. So your action's going to have a term that's like, well, you have the kinetic piece, And then you're going to be subtracting off a derivative of the field in every spatial direction, right? So you actually have a time derivative coming from the kinetic energy, and then you're going to be subtracting off all these spatial derivatives here. There's only one time derivative. Oh. Yo.
Phi is the field amplitude, right?
The what?
The field amplitude.
Phi is a field, yeah. It's just this.
So why is the time derivative of the field amplitude a kinetic energy?
Well, it's just, this is a kinetic energy, right? 1/2 mv squared.
Yeah, because Q is a position.
Yeah.
But phi isn't a position anymore. Q has units of distance.
Are you asking me if it's an actual energy, like in the units?
So what does it represent? Like how I don't really get the translation Q to phi and I to x, because Q is position for particle I, but then phi is amplitude at position x.
I think it's like if you have a medium that has a wave in it or something like that, that wave has a velocity and so on. I mean, I think it's just, it's the same interpretation. You can have a kinetic energy of the amplitude of something, right? So it's just it's not the same kinetic energy of a particle, but I think it's still a valid way of saying a kinetic energy. Yeah, I don't have a better answer. The field, the thing you should think of the field as. So if you say you have an Ising model, you'll do this on your assignment, and the Ising model spins up and spins down on a lattice. Okay. Now imagine somehow you're doing an ensemble average of all the different positions at a certain temperature, of all the different states. Sorry, and you have many ups and many downs. And in some parts of the lattice, these things average to 0, say, because you have ups and downs. In some places, they all stick together. Phi is like the average value of that, in space. And that average value can actually be time evolved too. And so is that a kinetic energy? I mean, yeah. Right? I think it's a little more abstracted, but I think the philosophy is a kinetic energy. So I want to do this subtraction, right? So I've taken Q's. I've taken this to S of 5's now. Time integral. I'm just doing this in 2 dimensions for some reason, and the argument is always it's something I'll call the Lagrangian. Okay, so I have this factor of the mass out front. Oh no, that's all squared. Right? So it's 1/2 mv squared, right? I have interaction terms, so I have derivative terms. I'm just going to write these as minus. All those minus signs and constants and stuff, I'm just going to absorb into a row. And this has the space derivatives. So one for every dimension on your integral here. So x, y. This one has to be squared. And then I'm going to subtract things off. I don't know what to use here for. I'll just call it, I don't know, u. All these terms, like the fields squared, and then I can have higher order terms. But you get the idea. The important part is going to come out of these first two terms here. So I want to rescale these. So they're just parameters. Okay, so these involve, what was it called? This H here. Whatever that, whatever that interaction parameter is, it'll define rho. Oh, and delta, right. Okay, we know what sigma is, so I'm basically just throwing away all the microscopics, as you can see. And that's what the field theory is. You're basically throwing away all the microscopic details. And you're just keeping terms that arise from symmetries. So let me get rid of a few more of these. Okay, the field's already an abstraction somehow. Right? It's a it's a description of the particle's state in real space. And so let me rescale phi by what? Phi over root sigma. So I'm just taking this mass per unit area, and I'm just absorbing it into the field. And I've defined a new constant, c squared. Okay, so I'm just messing with constants. And the Lagrangian now contains the derivative with respect to time squared minus c squared Why did I call that thing C? Because what? Yeah. So, yeah. You already took field theory. That's the action for special relativity, right? And sees the velocity. It's got the dimensions of, if you go through all this, you'll see it has the dimensions of velocity of my field.
Can I ask what happened to the nearest neighbor restriction?
The nearest neighbor, what? Sorry?
It's nearest
restriction? Yeah.
But here this integration is all space.
Right, so anything past nearest neighbor, I'm just including in these dots here. I don't know.
The nearest neighbor basically gives you the first derivative.
Yeah. Gives you these pieces here, right? Yeah. And then you'll see there's the other, there's the phi squared here. So you're taking a derivative over both x and y directions. And so that field has to be defined in, it's for like the finite difference in both directions on the lattice, x and y.
But how do we know there's an advantage? Here we just eliminated the summation.
Mm-hmm.
Here we should verify the ellipsis is dimension.
Right, so I mean, philosophically, it depends on the form of your V, right? So when you're given this V from either a microscopic consideration, like I have a Heisenberg model or something like that, then you'll know explicitly, you can confirm explicitly if you only have two-body interactions that all ellipses are zero. But more generally, the philosophy of field theory is that you're constructing an action based on symmetries. And so those ellipses may or may not be things that you want to include in it. So you're given the freedom to include higher order terms. I know it doesn't, maybe might not be that satisfying since we're coming from sort of microscopics, but that's the philosophy behind the field theory. That's what the point I'm trying to get out.
But I think it's more natural. It should be dealt with H by H I J. But
sure. So on assignment 4, not the one I'm going to give you today, you're going to derive this explicitly for an Ising model, and you'll see exactly how you translate in all of its gory detail this thing into the parameters in the psi-4 theory. Yeah, that question will be answered, and you'll be mad at me about it. So generally, because I've just been willy-nilly throwing all these, things around and dropping H's and not caring how they, the actual derivation, the explicit derivation of psi-4 theories from microscopic Hamiltonians can be quite hard. So that's why it's an assignment problem. So I don't have to deal with it. So this is the action for special relativity. C has the dimensions of velocity. So it's like a phase velocity or something in the system, right? Yeah.
So it's essentially you start with something that is non-relativistic and then like Lorentz symmetry emerges.
Yeah. So these types of theories are Lorentz invariant. Yeah, and they continue. So when somebody says you have a Lorentz invariant theory, that's all they mean. Basically this here. You can set your C to 1. So quantum critical points that are dynamical scaling exponent Z equals 1, Lorentz invariant conformal field theories, they have this Lorentz invariance that Z equals 1. So it's telling you there's a symmetry between space and time in the theory. If you scale space a certain way, then you have to scale time in the same way. So again, part of what I think we're doing in this class is trying to develop basic literacy in some of these field theory concepts, And so this, I think, is one important one. This idea that you have this emergent Lorentz invariance. So that's the Lorentz invariance is just built into the system. So to get non-Lorentz invariant psi-4 theories, you have to come from a different starting point in some sense. So let's set C equals to 1, because who cares? It's just a velocity, and then we can just finalize this action. Okay, I'm going to use relativistic notation here, so I'll define this in a minute. Okay, I'm going to keep the parameters in front of everything. I called it U there. That was a mistake. I'm calling it R now. Everything's been rescaled somehow. So my phi squared term is going to have R. Sometimes you'll see an M there, a mass. But let me talk about that later. I already have a mass up there. I don't want to confuse things. U's. I could call it U2 actually. Why not? U2. I could have, okay, what's in those ellipses depends on the form of that V. There's nothing stopping, I don't know, a phi 3 term or a psi-4 term. I don't know. All right, just keep it going. I'll talk about those terms in a minute. This del phi, that's the Lorentz invariant action thing that I wrote. You'll forget what this means. I guarantee it. You'll be looking at one of these actions someday and you'll be like, oh, what the hell is that first thing? So I've set c equals to 1. In 2D, it looks like that. I wrote this in general spatial dimensions. So there's higher order terms. So this illustrates another sort of assumption in the notation of these field theories, is that the integral over time and the big D integral over space are combined to just look like this. And so you have to remember that one of those integrals is time and the rest are space. So when you hear people talking about, field theories, maybe scale invariant theories, conformal field theories, they're talking about D+1, right? This is the reason why. So if you have a d-dimensional physical quantum system, whatever that is, and if for some reason you're justified in writing this field theory, the field theory is in a higher dimension, right? That higher dimension is the path, the Euclidean time for the partition function. It's the t. And so the notation of the theory, modulo this definition, which gives you some idea about the dynamics, the space-time relationship, is just is a field theory in a higher dimension. So this is very powerful. It allows you to take a quantum system and solve just a sort of classical field theory in one higher dimension and get many interesting properties out. So how do you can just write down this. People will start, you can start a paper with this. You can just write down this action and say, I want to study this action. And the justification for studying it comes from you. Is it because there's certain terms in this potential, or you had a critical point that has the right space-time properties? So typically what you do is you restrict these terms by symmetries. Okay, so actions are in the field theory sense often just restricted by symmetries. In condensed matter, these are often called Landau theories. So for example, symmetries constrain the action. So one common one is that your field value, your action has to be invariant under multiplication of your field value by -1. What is that? Is that time reversal symmetry? Field goes to minus field. So you might know something about your system, just the fact that maybe there's no magnetic field and your Hamiltonian has a certain symmetry, like a time reversal symmetry. So if you require invariance of the action, under phi going to minus phi, then you can just write this thing like this. dd, okay, so we have a half full front, okay. I don't know, what did I, b4 over 4 factorial. So you might say the simplest psi-4 theory that describes this symmetry, invariance under this symmetry operation, wherever that comes from physically, could be this. And this is basically the simplest psi-4 theory you can write.
You in principle have infinite number of terms that satisfy your symmetry, right? So
yeah, so you also have higher order terms, right?
Right, so you need like an extra argument to kill higher order terms.
And that argument comes from the renormalization group usually. Those higher order terms are irrelevant, but you don't take that till 705. Yeah. So also they're way harder to include perturbatively, which is what we're working towards. So psi-4 is hard enough. So this is a simple psi-4 theory. If you had an important symmetry like a magnetic field, then you would have to add a term that makes the Hamiltonian not invariant. Does that mean variant? I don't know. Under that symmetry operation. So if you're imagining that you maybe have spins on a lattice, you've taken the continuum limit, but then you have a magnetic field. Instead of worrying about the microscopic interaction of how that magnetic field specifically works on the spins, you can simply study it by adding a phi term. To phi. So that's just an example. So you should be wondering about the regime of validity of all this. I mean, field theories aren't what was the quote that Rajiv Singh said to me? It's like there's more under heaven and earth than what's contained in your field theories. Because we get used to building intuition about our problem from these psi-4 theories. But you have to always keep in mind, why are they valid? When are they valid? And this can be the most difficult part in working with these types of theories. Well, so one way to address this is to take the microscopic condensed matter system that you're interested in and like literally and explicitly derive the psi-4 field theory. You can derive it from the microscopic Hamiltonian. Assignment 4, I think you'll do that in question 1. But we need a few more tools before you start doing that. So you'll actually just work on the classical Ising model, which is something we derive explicitly in 705. But you'll be looking at how all these parameters of your psi-4 theory relate to the actual Hamiltonian terms. Even if you do that, you know, or even if you're basically building an action based on symmetries, you really need this continuum thing that I just erased. You need this continuum limit to somehow be valid, which means, which really means the physics of the system can't depend somehow, for some reason, on that lattice length scale. Okay, and that's harder to justify. Ignoring delta, the ultraviolet. So if you construct, so say you forget the lattice models. If you just constructed a continuum field theory based on symmetries, you would say, what the hell's delta? You know, I just have fields in the continuum. This thing you would call the UV cutoff, because it would cut your integral off in the short wavelength regime. So the ultraviolet, they call it. But for condensed matter, when you're starting from a microscopic Hamiltonian, this thing is equal to like A, the lattice spacing. Okay, so in either case, you have to say, why am I justified in ignoring that, or why am I justified in ignoring the physics that comes from that lattice length scale? So this basically requires so this requires a correlation length, which is a measure of the characteristic length scale of correlations in the system. So if I have a spin sitting on a site here and a spin sitting on a site here, you know, how far apart do I have to remove that second spin before it doesn't feel the effects of the original spin anymore? That's the correlation length. So you basically require a correlation length that you know, say is much, much bigger than delta. And I haven't defined exactly what a correlation length is, but it's, you know, this is the entire subject of 705. So we basically have an entire lecture on, we have an entire course on the correlation length and the consequences. And just as a spoiler or an advertisement for that class, you know, this occurs near phase transitions. Say, and you can make a quantitative. Yeah, you can make a quantitative connection between things derived in the field theory and microscopic numbers or quantities arising from the Hamiltonian at continuous phase transition, both quantum and classical. So there's a regime, like in the transfer field Ising model, there's a regime where basically the droplets, say the minority droplets, become much larger than the lattice spacing. And so in that perturbative picture that we've developed of droplets, that's kind of the regime where that's valid, and that occurs near the phase transitions. Okay, so remember you have a droplet, you flip one, you flip the other, a whole bunch of, you're flipping all these droplets, they get bigger and bigger. There's some free energy balance, energy versus entropy of these droplets, and the droplets proliferate at some point, and that point where the droplet proliferates is where the size of these minority droplets gets big. You can't define the minority phase uniquely anymore. That's actually the phase transition. And at that phase transition, the characteristic length scale, which is just the size of those droplets, is much bigger than the lattice spacing. It actually diverges. And so this is when these continuum theories really become justified. So that's that has to do with the renormalization group and all this other stuff. So I recommend you take 705 to really understand what's going on with that. 705 is just advanced statistical mechanics. There's not a lot of talk of quantum mechanics in it, but we developed the same kind of almost idea of a path integral for classical stat mech systems. Okay, that's enough of that. So now we have a psi-4 theory, and like I said, the power, there's two reasons we study field theories that I know of. One, you can calculate correlation functions, and these correlation functions are like the green function, they're the things that are experimentally relevant. You can get ideas about, the quasi-particles from the poles of the Green's function and so on. You can get, so the quasi-particles have a dispersion, there's an energy associated with excitations out of the vacuum. That's all contained in the 2-point correlation function and the higher endpoint correlation functions. So we can calculate those, and we can also calculate them perturbatively. So when we have the interacting term, right, so when you have a term that comes from the interactions, we'll see that we can do a perturbative expansion of the action in order to calculate these correlation functions more easily. So that's what we're aiming for. So it's the expectation value of fields like this. I don't know. So I'm going to label, I don't know. So I have all these different coordinates. I don't know. I can have many fields. We'll basically look at 2-point and higher point correlation functions. I'll define this later. And those are sort of the overall goal of this type of approach. So I want to develop a strategy for this. And we're going to start that strategy by throwing away terms in this action that aren't Gaussian, and we're going to perform Gaussian integration on the rest of this. Okay, so if we only include terms up to 5 squared, we can solve this problem exactly. Who knows what the Hubbard-Stratanovich transformation is? You gotta sit through it again. Because you're the only one. Okay, so we need to develop basically the general theory of Gaussian integration. And it's completely standard. Every field theory course and every advanced stat mech course will go through this same treatment of Gaussian integration. So I'm going to try to do it quick in half an hour. And If you still have questions, you must read the literature. Okay, so the goal is we learn how to integrate Gaussians of this form. Now you're worried. I mean, this is like, it's a functional, right? These are functions of x, and we have to perform an integration over many variables, and each one of those variables is a function. So we need some sort of functional way of doing this. And yeah, let's just do it. If you work on non-interacting field theories, everything's Gaussian integration. Everything can be done exactly in principle. So let's start simple. Let's start in 1D. So you can see the strategy for how these Gaussian integrals go. Let me define two real numbers. And I think A has to be greater than 0, probably. Okay, so let me define an integral. Okay, so you would just plug that into Mathematica immediately. But it's so simple. Okay, so it's x squared and x. So we want to be able to deal with fields, and field squared. That's the idea behind this. The same two basic steps, I think, occur in all Gaussian integrations of this form. Is this completing the squares or uncompleting the squares? I don't even know. It's one of the two. So now this thing's squared. And what you're going to do is redefine the field or the x variable to be this thing within the square. And that takes this thing out in front of the integral. Be careful with your limits of integration, but not really because they're infinity. And then you have that thing that's just x squared with a constant out front. And that's it. You can't do anything more. You have to plug that into Mathematica. So that'll give you it's a over 2, so it's 2 pi over a. And then that e to the j squared over 2a. Yeah, that's right, plus. Yeah, good. Watch me, I'll randomly put minus signs in front of everything in the exponential, because I'm used to writing e to the minus beta h so many times in my life. Okay, same philosophy for, okay, so that's like one variable, that's a couple real numbers. Now we want to go to, the n-dimensional case. So my a's and j's aren't the same thing anymore. A is going to be like the interaction matrix or something like that, or the a matrix that defines, I shouldn't call it interactions, but a matrix that defines the relationship between i's and j's, between different fields. So we can assume that it's symmetric. It's going to be real and symmetric for this case. And that has to be justified by the microscopics, but it's true for any Hamiltonian of reason. So it's real symmetric. You have to be able to invert it. Invertible? I'm not sure that's mathematically necessary. And we're in n dimensions, so it's just going to be n by n. And then your j's are just vectors. Okay. So I'm just calling that A. I guess I should put an arrow over my J. So then your n-dimensional version of this Gaussian integral, AJ, and J arrow. Okay, so you have all these different variables x now. So you can write this different ways. With summation conventions over repeated indices, or I'm just going to drop all those indices. And you know, the way the summation convention works, this has to be, so this is a vector, but you have to transpose it. And then this thing on the left, in this dot product, if you will, is just the transposed J. So I'll write that like T dot X. So that's vector matrix vector. That's vector vector. Sure. So that's the integral. I'm defining that integral. That's the thing I want to solve. Okay. So as before, we can start by redefining the integration variable. That's kind of, let me write x equals y something. So we're shifting this integration variable. So in this case, it's a vector, which I will shift by A inverse and J, where this is just the transpose. Everything's symmetric. Okay, so then the thing that occurs in the exponential, so x vector, A matrix, x vector. First one's transposed. Is just, I'll write it like this. It's transpose of y. So that's x, A, and then x again. A, I'll write it like this. Okay, so you just have to keep track of the order of these things. because they're matrices and vectors. Okay, so every time the inverse is multiplied by the matrix, you'll get the identity matrix. So just go through this quickly. I'll remind you these are dots. Then I'll have the transpose dot J. Yeah. And then the transpose and the non-transpose J. All right, that's looking ugly. Okay, so that's XAX. So with that same shift of integration variables, I can write the vector, the second piece, the transpose JX, which will be J, must be transpose, right? Y, right? J transpose A inverse J. Yep, okay. So now I can use this to write the argument of the exponential. That's all I'm doing. I'm just doing the same step as for the one-dimensional case, basically. So then the argument of the exponential is so take the top, or minus half of the top, and add it to the bottom. So minus half of the top gives you minus 1/2 of these two terms, but they're dot products. So the order doesn't matter. And you're adding this thing, so that cancels, and that's like the simplification. Wow. This might seem boring, but I guarantee you'll be looking at this when you do assignment 4, and you're like, what's A, and how does this relate to the Ising model? Okay, so my integral has now an integration variable that's y, and it has this constant piece, if you will, in the argument, which is the analogy of what happened in the one-dimensional case. So you don't have to worry about integrating over that. You pull it out front. So pull it out. J transpose A inverse J. Right, and then the integral, which is over y now. A, y. Yeah, that seems right. Okay, so you're done. Except, what the hell is this thing? It's not just root pi, 2 pi over A or something, because A is a matrix, right? So you can't plug it into Mathematica and you quit, or I mean, why do you need this? This is the analogy of the many-body Gaussian, right? So all the vectors will be all of over all the indices of your particle, say, positions, and the A's are all the terms in the Hamiltonian, blah blah blah, right? So you basically need to know how to do this type of Gaussian. So if I said this part J equals to 0, I'm asking how do we do this thing? Y. Oops, Y. Okay, so to solve this thing, what you do is diagonalize A. A is symmetric. I assumed it's symmetric. It means you can diagonalize it with orthogonal matrices. Did you know that? I didn't know that until I did this the first time, I guess. So it's symmetric, so it's O, you know, it's two orthogonal matrices where the transpose is the inverse. Diagonalizable. Diagonalizable. I guess that's important when you have to worry about the Jacobian. So let me call O. So it's real. The transpose is the inverse. So O transpose A, O. We'll call that big lambda, which has eigenvalues small lambda. I don't know. So it's diagonal. So we're going to try to write this Gaussian in terms of all of those eigenvalues. And I'm going to have to transform my vectors. And so if I have a vector x, and it's orthogonally transformed, I'll say it's just matrix vector multiplied. So I define this V, which is O times, sorry, x is O times V. Then I'm worried about the Jacobian here, right? But in this case, so the Jacobian, let's see, so it should be, yeah, so it's that. It's dx is the determinant of d. Yeah, that's the right order. But since it's orthogonal, that's 0. That's 1. So we have just symmetries in A, essentially, that allow us to not worry about the Jacobian at this stage. So then, let's see. Just with some vector x, which is V transpose, O transpose, reverse the order. Remember, A, O, V. All right, there we go. So now I'm diagonalizing A. So a V transpose, that matrix, big lambda, V. That's diagonal. All right. So I'll write the sum explicitly. You're summing over repeated indices. You have all the eigenvalues, and you have V from each side. So it's lambda V squared. And summation notation, just lambda I VI squared. Okay. That's it. You're done. Oh, I used x's. Oh, well, whatever. So I can just plug this into the integral we're trying to solve. No Jacobian. E to the minus 1/2. I'll put the sums in, or else I'll forget. VI squared. Okay, so that sum I can pull out as a product. So I'll have a product of integrals, which is nice. Because then I can just use that integral expression that I know. But a product that's over all these eigenvalues. So if I take that product, I'll get 2 pi for every element in that product. So it's 2 pi to the n. And then this is just the determinant. This is equivalent to the root determinant of A. No, it's 1 over the root. So it's minus 1/2. Okay, so in principle, you have to know that object in order to do this Gaussian integral. Lambda I. But I can also write it as an exponential. So also, I think you'll usually see things written like this. So I just exponentiate that sum. Okay, so however you want to express that determinant, basically. It's up to you. So that'll be related in the Ising model when you do your homework to like the JIJs or something like that. So it's related to the microscopics. So all I'm saying is if it comes out, I'll write the full thing. Okay, so that integral and don't forget out front you have JAJ. That's a J, right? So that's sort of the n-dimensional generalization of the Gaussian integral. We have all these n, variables occurring in the system. You have to do one more step and generalize this to functional integrals, but it doesn't change very much. I think you just have to really go through this once in your life and then start doing it. Start using that result. So hopefully this is a once or twice you've had to do this in your life. Okay. Every textbook on many-body theory has this laid out. It's just completing the squares, doing this substitution, and then in the case where you have this n-body case, just being careful with how you treat the matrices that are all your interactions and parts of your Hamiltonian and so on. So that's Gaussian integration. That's the tool we need for calculating expectation values. And we'll take the the Gaussian theory, so the phi squared theory, and we'll start working on calculating the expectation values, I guess, when we come back after the break. And then we'll perturbatively include effects from the psi-4 term. Okay. So that's the plan. No class next week because you're lazy. Give me, and also I'm lazy. Give me your homeworks, and here's your homework 3, which is due in 2 weeks. But since there's a break, there's only one question, but the question's really hard. So, okay, and it's on the Dropbox. Hopefully, the right version this time. Okay, so no class next week, and I'll see you on Tuesday, the week after reading week.